Hello, glad to have you along. Alright, in our last video we were learning how to graph circular functions, and we learned how to graph the functions y equals sine x and the function y equals cosine x. And what we're going to do here is just kind of continue along that vein, and we're going to learn how you graph y equals tangent of x. Alright, now the graph of y equals tangent x is going to be a periodic graph, kind of like the graphs of sine and cosine were, but there's going to be definitely a couple of major differences, and you're going to see those as we try to graph the function. Now, let me actually put a grid here. What I have here in the bottom corner is a unit circle again, but this time rather than showing you the cosine and sine values for a function based on its radian angle measure, I am showing you the tangent values at around the unit circle. Alright, so for instance, here's the tangent of pi over 6. It's a value you know. Tangent of pi over 4, tangent of pi over 3, and so forth. Okay, now just like with the other functions, what we're going to do is we're going to let an angle measure be the input value for our function. So x is going to be an angle measure, and it could either be measured in radians or in degrees. Because of the input values that you see here, you can tell that we're measuring in radians, just like we were in the previous video. And then the output values, or the y coordinates, are simply going to be whatever the tangent of each of those angle measures are. Alright, now one major difference between the graphs of y equals sine x and cosine x compared with the graph of y equals tangent of x is the fact that the tangent of an angle is not defined for all numbers. Okay? If you recall, there are a couple different places on a unit circle where the tangent is undefined, and that happens to be at pi over 2 and at 3 pi over 2. And the reason it's undefined there is because the cosine of each of those angles is 0. And so when you divide the sine value by the cosine value, you get an undefined expression. Whenever you're graphing a function and it has certain values in its domain that it is undefined for, remember that you get vertical asymptotes. Well, so that's one major difference here, is that the graph of y equals tangent of x is going to have vertical asymptotes. Alright? And for now, I'm going to put those vertical asymptotes at pi over 2 and at 3 pi over 2. And then I'll show you how to figure out where the rest of them are as well, because there are more. And in fact, let's talk about where another one of those is immediately. What I'm going to do is I'm going to try to find a place or a section of this unit circle here that has all of the possible values of tangent of x consecutively without having any values where it's undefined. Alright? Hopefully that makes a little bit of sense. And the first place that you typically look on the graph of, on the unit circle, when you're looking for places where the tangent goes through all of its values without hitting any undefined values, is between negative pi over 2 and positive pi over 2. Okay? So, you agree that this is negative pi over 2 here, and that the tangent of that angle is undefined. Well, that means I'm going to go ahead and put a vertical asymptote here as well at negative pi over 2. Alright, so we've got some vertical asymptotes there. The next major difference is that the period, the range of values over which the y coordinates repeat themselves, is a smaller range of values within y equals tangent of x. Remember with sine x and cosine x, you had to go all the way around the unit circle from 0 to 2 pi before you had the pattern of y coordinates start repeating themselves. Not true with with tangent. It turns out that each half, the left half and the right half of the unit circle, contains a full cycle of the values of tangent. You can see this, you have undefined here, and then you go to negative square root of 3, negative 1, negative square root of 3, 0 over 3, and so forth. Positive square root of 3 over 3, 1 square root of 3, and then you get to undefined. And then when you get on the other side of pi over 2, you start repeating with those exact same values, negative square root of 3, negative 1. Okay, all the way to positive square root of 3 over 3, 1, and square root of 3, and then back to undefined. So a period for a tangent graph is only 1 pi radians long. It only takes half of the circle to go through all of the tangent values that you can get. And it will be important for you to know that as we move forward in the remainder of this chapter. Alright, now let's get to actually graphing that cycle of values. All right, and we're going to start with graphing the cycle between negative pi over 2 and positive pi over 2, that unbroken cycle of values for a tangent. Now, to make it easier to follow the numbers that I'm going to start plotting on our graph here, I'm going to go ahead and write the decimal approximations for the square root of 3 and the square root of 3 over 3 over here. That'll help you see where the y coordinates are that I'm graphing. All right, and now watch as I go ahead and make the graph. We already got the vertical asymptotes in place at negative pi over 2 and positive pi over 2. So let's kind of go counterclockwise between the two and go through all the y coordinates that we get. Well, the tangent values that we get. The tangent of negative pi over 3 is negative square root of 3, or negative 1.73. Now negative pi over 3 is going to be somewhere around here, and negative 1.73, let's say that this is where that's going to go. And then as we get to negative pi over 4, which is halfway between, which is halfway between 0 and negative pi over 2, the tangent is equal to negative 1, correct? So there's negative pi over 4, comma negative 1. And then at negative pi over 6, which is between, not quite halfway, but between negative pi over 4 and 0, you get negative square root of 3 over 3 for the tangent value, or negative 0.577. So somewhere around here would be that value. Now continuing on, the tangent of 0 radians is equal to 0. The tangent of pi over 6 is about 0.577. The tangent of pi over 4 is 1. And the tangent of pi over 3 is the square root of 3, or about 1.73, so somewhere around there. And that's going to be a sufficient number of values for us to be able to actually plot this tangent graph. Now remember, another difference between sines and cosines and tangents is that there's no limit on the value of tangent. Whereas with sines and cosines, you can't get anything less than negative 1 or greater than positive 1, correct? Tangent, the range is anywhere from negative infinity to positive infinity. And what we're going to do then is we're going to trace the branch, this branch of the graph, through the points that I just created there that shows all the possible values that tangent can get. And it does keep on going up forever, and it does keep on going down forever between those two vertical asymptotes. All right, that's the graph of one cycle of the tangent function. And then as you continue past pi over 2, you get the same values over again until you get to 3 pi over 2, like so. All right, and then we can keep continuing that every pi units. So between 3 pi over 2 and 5 pi over 2, you get that cycle. And between negative pi over 2, if I'm going to the left now, between negative pi over 2 and negative 3 pi over 2, you get that same cycle of values. So there you have it. That's what the graph of y equals tangent of x looks like, and you can see how we use the unit circle in order to create that. Thanks for your attention. Good luck working with this stuff. See ya.